So good afternoon all. So this week's tutorial, for this week's tutorial, we have only two questions, right? Basically, you just need to prove certain aspects, right? So let's start. Just before I start, let me just send you the solution in the chat box, right, for you guys to access. Okay. So the solution set is already in the Dropbox. In the chat box, right? So you can use that to follow through. Wait. Okay, so let's get started. Question number one is to gain. Question number one: the gain of a certain amplifier amplifier is a function of frequency a j omega, which is equal to -16 times 10 to the power of 6, right? Upon j omega. A feedback path connected around it has a beta, which is equal to 10 to the power of 3 upon 2 times 10 to the power of 3 plus j omega, whole thing squared, right? Will the system oscillate? If so, at what frequency? So we basically need to have to use the Bokosian criteria for oscillation, right? So let's just quickly go over it. So under the Bokosian criteria, okay. Okay, the criteria says that the criteria says basically the amplitude, right? The amplitude of A times beta should be equivalent to 1, and the angle of A times beta should be equivalent to 0 in order for the oscillation to take place. Okay. So based on the Bokosian criteria, what we need to do is check if these two systems, the open loop gain and the feedback gains are given over here. So we have to check whether this feedback system is going to oscillate or not, right? So the first thing is we have to compute, because we in this particular case, right, based on the formula, right? Sorry. Okay. Based on these particular two conditions, we have to calculate A times beta, and then we can compute the magnitude and the phase from it, right? So basically calculating A times beta, that is going to be basically equivalent to -16 times 10 to the power of 6, right? -16 times 10 to the power of 6 upon j omega into 10 to the power of 3 whole thing upon 2 times 10 to the power of 3 plus j omega, the whole denominator squared, right? So the whole denominator is squared. So basically we will be left with -16 times 10 to the power of 9 whole thing upon j omega into 2 times 10 to the power of 3 plus j omega, whole thing squared, right? So this becomes our A times beta. Now the next step is to calculate, right? We have to calculate the phase of the system, right? So to determine if the system will oscillate, we will first determine the frequency, right? If any, at which phase angle of A times beta, right, equals to 0 degrees or a multiple of 360 degrees, right? Using the phasor algebra, we have to find the phase of this particular term that we have just derived, right? Or the loop gain that we have calculated, right? Now calculating the phase of this, right? If we have to calculate the phase of A times beta, so what that is when we are based on the polar properties, right? So if you use the polar properties, then it will be the angle of whole of this A times beta, right? The angle of A times beta, this is what we have, right? Is basically equivalent to, if we're multiplying two things, right? We basically add the angles. If we are dividing, we subtract the angles, isn't it? So in this particular case, -16 times 10 to the power of 9, right? We can just directly find the angle over here. So the angle of -16 times 10 to the power of 9, right? So the negative sign is missing over here. Then we have to, let's say we can break this, right? 1 upon j omega could be separate. So that will be plus angle of 1 upon j omega, right? We can factor this. and then it will be equivalent to plus angle of 1 upon 2 times 10 to the power of 3 plus j omega whole thing squared, right? So in that particular case, we are saying basically negative 16 times 10 to the power of 9 times 1 upon j omega times 1 upon 2 times 10 to the power of 3 plus j omega whole thing squared is basically equivalent to this, right? So uh, so once we have this, right, once we have separated the angle part, then we can find the angle, right? The angle over here at the numerator and the denominators, right? So that is what we have split up over here, right? We have simplified it using the polar properties. So now the angle of negative 16 times 10 to the power of 9 is going to be 180 degrees or negative 180 degrees. What do you think? Guys, you there? Okay, so what do you think? The angle should be angle of negative 16 times 10 to the power of 9 will be? What do you think? Negative 180 degrees or 180 degrees? Okay, it's going to be the same thing, right? Whether you use 180 degrees or negative 180 degrees, it's going to be the same thing, right? In short. So let's say if we are supposed to measure the positive angle, so we can take the positive angle. So we will just take 180 degrees, right? If we consider the angle of this to be 180 degrees, so it will be 180 degrees minus the angle of 1 upon j omega, that is also same as negative j times 1 upon omega, isn't it? If we take the j on top. So in that particular case, what happens? The angle of negative j times 1 upon omega is basically negative 90 degrees, right? So the angle of that is negative 90 degrees. Then minus, right? When we have the vector over here, uh, since this particular part, the denominator is, I mean, like if we find the variable, it's 1 upon something, right? So basically what we can say is the this is same as 0 degrees minus the angle, right? Okay. So in that particular case, the angle of this will be, the power will come in front of the angle. So it will be, since it's in the denominator, so it will be negative. The power will be in front, right? We will be basically multiplying this power with the angle that we get of this value over here. That is 2 times 10 to the power of 3 plus j omega, right? So 2 will come in front. And then we take, to find the angle of this, complex number, it will be basically equivalent to the imaginary part, that is omega, right? The imaginary part is the omega. So omega upon the real value, that is 2 times 10 to the power of 3, right? So we have the angle formula over here. Now what we need to do is the unknown variable of, in this particular case, is omega. Remember, the angle of a times beta should be equivalent to 0 degrees, right? So if we equate this whole term to 0, right, and then if the other side is 0, so basically that will be 0 is equal to 180 minus 90 degrees. That is going to be 90 degrees. Okay. So that is equal to, write it over here, that is going to be basically equivalent to 90 degrees minus x, right? In that particular case, the x is this whole term over here, right? The angle value that we have for this whole term. Okay. And then what we can do is we can take this particular x value to the other side, right? So in that particular case, we'll be left with 2 arc 10 of omega upon 2 times 10 to the power of 3, which is equivalent to 90 degrees, right? The other way around is that if you had used negative 180 degrees, it would have been negative 180 degrees minus 90 degrees. That is going to be equivalent to negative 270 degrees, isn't it? So negative 270 degrees is also equivalent to 90 degrees, right? So it does not change the value, right? It remains the same thing. So once we have this, then we can solve for omega. If we solve for omega, we'll be getting omega is equivalent to 2 times 10 to the power of 3 rads per second. Now we know the omega value, right? We know the omega value. The two conditions that the open loop gain should satisfy in order for the system to oscillate is the magnitude should be equivalent to 1, the phase should be equivalent to 0, right? So we have solved for the phase over here. So in order for A times P to have a phase of 0 degrees, right, omega has to be equivalent to 2 times 10 to the power of 3 rads per second. Now we have to take this particular value and check whether we get our whether we get the magnitude of A times beta to be equivalent to 1 or not, right? So what we do is we find the magnitude, right? The magnitude of this A times B. So the magnitude of this will be basically the magnitude of A times B is basically equivalent to the absolute value of negative 16 times 10 to the power of 9 upon j omega into 2 times 10 to the power of 3 plus j omega squared, right? That is basically equivalent to the absolute value of the numerator, that is negative 16 times 10 to the power of 9, holding upon the absolute value of j omega, or the magnitude of j omega, times the magnitude of 2 times 10 to the power of 3 plus j omega squared, right? Now, what we can do is we can simplify this. This would be basically equivalent to 16 times 10 to the power of 9, right? As it is. Since it's just a real number, so the magnitude will also be that same value, right? So that it will be 16 times 10 to the power of 9. The magnitude of j omega will be omega only, right? So upon omega, and the magnitude of this will be basically equivalent to what will the magnitude be equivalent to? Anyone has any idea? Anyone has any idea what the magnitude of this is going to be equivalent to? What do we do with the magnitude? We square the magnitude, right? So whatever value we have, right? Whatever value we get, the magnitude of this inner term, it is going to be squared, right? So once you have this, I'm not sure whether this is going to be equivalent, right? 2 times 10 to the power of 3, all things squared plus omega squared. The magnitude of this is going to be basically 2 times 10 to the power of 3 squared minus 8 times p. Okay, it will be plus j omega squared, whole thing squared. Okay, it's right, right? The magnitude of these will be basically real value squared plus j omega squared, and then whole thing root of it, right? So okay, let me just show you the formula. Magnitude of a polar complex number. Okay, the magnitude of a plus bi, or in our case it will be a plus jb, is basically equivalent to root of a squared plus b squared. So in that particular case, what happens is this root sign, if we take the square of this whole value, right? Because we have this square sign over here, right? So what happens is this square, right? The square will cancel off with the square root. So we'll be basically left with a squared plus b squared, right? So in this particular case, our a squared is this particular term, right? And b squared is this particular term. So in that particular case, the magnitude of this 2 times 10 to the power of 3 plus j omega squared is equivalent to 2 times 10 to the power of 3 squared plus omega squared. Right? So once we have this particular value, the magnitude of AB, right? What we need to do is we have to take this omega value that we have over here that we calculated and substitute this value into this particular formula to see whether we get our magnitude to be equivalent to 1 or not, right? So in place of omega, we just need to substitute this particular value. So if you do that, you will get the magnitude of a times b equivalent to 16 times 10 to the power of 9 as it is, 2 upon 2 times 10 to the power of 3 into 4 times 10 to the power of 6 plus 4 times 10 to the power 6, which is equivalent to 1, right? It will come down, or it will be basically equivalent to 1. So in this particular case, it fulfills, right? We know that whatever omega value you got it after, using the phase formula, right? Whatever omega value you have, once you take that and substitute it into the magnitude formula, it satisfies both the conditions, right? When we calculated the omega value over here, we were when we calculated the magnitude of the phase of A times beta, we ensured that the phase of A times B is going to be equivalent to 0, right? And then once we have satisfied that condition, we took that omega and substituted into the magnitude formula of A times beta. And then we checked whether we are getting the magnitude to be equivalent to 1 or not. So in this particular case, we are getting the magnitude to be equivalent to 1, right? So both the criterions are satisfied in this particular case. Thus, the Barkhausen criteria is satisfied at omega is equal to 2 times 10 to the power of 3 radians per second. And the oscillation occurs at that frequency, right? Or the oscillation will occur at this particular frequency only, right? Based on the Barkhausen criteria. So you could have also done it the other way around. What you could have done is you could have found the magnitude of this A times B, right? The loop gain, the magnitude of loop gain equivalent to 1, and solve for omega in that particular case. And whatever omega you have, you take that omega and substitute it into the phase formula and check whether you're getting a phase difference of 0 degrees or not, right? You could have done it the other way around as well. But since the phase one is a little bit, computing the magnitude, computing the frequency value for a magnitude will be a little bit complex compared to the phase form, right? So that is why this particular step has been taken, right? So what you need to do is equate the phase, the phase of this, equate it to 0 and solve for omega value and take that omega and substitute it into the magnitude formula to check whether the amplitude is equivalent to 1 or not. If you get amplitude equivalent to 1, and you know that the Barkhausen criteria is satisfied at this particular stage when you are calculating the phase, in that particular case, it satisfies the Barkhausen criteria at that particular frequency, thus it's going to oscillate, right? Do you have any questions regarding this? Guys, you there?
No, sir.
Okay, I'm going to drop the solution in the Dropbox again. I think some of you joined in late, so just use that solution as a guide, right, in between, because this is a whole, what happens is, since I'm not writing on the board or anything like that, right, it will be a little bit difficult. So I've dropped in the solution in the Dropbox, so you can retrieve the solution, right? In the meantime, we move on to the second question. In the second question, for the network shown below, prove that the gain of this particular circuit is equivalent to 1 upon 3 plus j into omega RC minus 1 upon omega RC, right? This network is used with an op-amp to form an oscillator. Show that the frequency of oscillation f is equivalent to 1 upon 2 pi RC and the gain must exceed 3. So we have to basically satisfy the conditions, right? We have to show that the gain must exceed 3, and we also have to prove this particular formula. So in order to prove the formula over here, we just need to do a circuit analysis of this particular circuit over here. So just from this particular circuit, the first thing is to draw the current directions. Remember, when you're doing the circuit analysis, you have to draw the current directions, isn't it? Basic E102 fundamentals, right? So draw the current analysis, right? You can do your nodal analysis as well, but in this particular case, mesh analysis would be much appropriate, right? So draw the direction of the currents, right, in both the loops, since we are having 1 and 2 loops, right? 2 loops. So there will be 2 current, right? And this is the current direction that has been selected in this particular case, right? So once we have determined the current flow directions in both the loops, what do we need to do next? We need to write the current equations, isn't it? So the first thing, just from this observation, we know that VF, right, the voltage VF, or the output voltage VF, is basically the voltage across this particular resistance over here, right? So in that particular case, VF is basically equivalent to I2 times R, right? So VF is basically equivalent to I2 times R. Next is the capacitance values will be given. So the impedance of a capacitance is basically given by 1 upon j omega c, right? So in that particular case, you can say that your impedance XC is basically equivalent to 1 upon omega c, right? You can forget about the j. J is going to basically indicate whether it is a active element or passive element, right? So in that particular case, I mean, resistors and capacitors and inductors are passive elements, right? So basically Xc is basically equivalent to 1 upon omega c. Next is to write the loop equations for both the loops. So writing the loop equations for both the loops, you'll get V out is equivalent to, right? If you start from this particular line, V out is equivalent to I1 times R, right? I1 times R. Remember, there's a J, so this J, whatever, like Xc, if it was, what do you say? Let me erase this. Okay. So let's say the impedance, right? Impedance of a capacitor is basically given by 1 upon J omega C, right? So what happens if you consider 1 upon omega C to be equivalent to Xc? The J will go up, right? So that will form negative J. So we are left with just 1 upon omega C, which is equivalent to Xc. So it will be minus Xc, isn't it? Just excuse me with the writing. So 1 upon J omega C is basically equivalent to, remember this J goes up, so it will form minus J, and 1 upon omega C is basically equivalent to Xc, right? So knowing this, right? Knowing this, what we need to do is when we go across the capacitor, it will become, as it is, it's a minus, so it will be minus J, right? Minus J times Xc times the current flow. That is, remember, if we are considering this particular loop, and if we are writing the equations for this particular loop, we have to assume the current flowing in this particular mesh is greater than the current flowing in this particular mesh. So it will be basically I1 minus I2, right? So the loop equations for this has been written now. Now we move on to the second mesh, right? Second loop. So the equations for the second loop, right? In this particular case, we start from, let's say, let's start from this particular capacitance, right? So remember, if we are considering this particular loop, what happens is we consider the current flow in this particular loop to be greater than this particular loop. So it will be I2 minus I1, right? So I2 minus I1 times the impedance of the capacitance, which is equivalent to minus J times Xc. So minus J times Xc into I2 minus I1, right? Minus, then we move on to the second capacitor. Once we have written the equation for this capacitor, we move on to the second capacitor. So that will be again, remember, the current flow in this particular case will be basically I2 times the impedance of this capacitance, that is I2 times minus JXC. So it is going to give you minus JI2 XC. And then we come across this particular resistance that is going to be plus I2 times R, which is equivalent to 0. Okay. So once we have the equations, right? Once we have these equations with us, the loop equations, this is loop 1 equation and loop 2 equation, right? And this is just visually inspecting the circuit. We know that VF is basically the voltage across this particular resistance. So that is equivalent to I2 times R. And then we know that the impedance of the capacitance is basically given by 1 upon omega C, right? So in this particular case, what we can do is from equation 3, right? From this particular equation, what we can do is we can make I1 the subject of the formula. So that is going to be equivalent to V0 minus minus j I2 xc upon r minus j xc, right? Then what we can do is once we find our I1, we can take this I1 and substitute it into the second equation, right? This is the substitution method to solve for our equations, right? So once we have our I1, we can take this particular variable and substitute it into 4. So when you substitute I1, the I1 value that we calculated over here into equation number 4, we get our I2 to be equivalent to this particular term over here, right? So we can further simplify this, right? We can further simplify this and we get this particular term over here. So we know our I2 and we know our I1. Remember, our I1 is in terms of I2, right? So in order to find your I1, you can also take this term and substitute it in place of I2. So once we have our I1 and I2 values, right, we can find our VF upon V0. So in order to find VF, okay, in order to find our VF upon V out, we can use equation number 1. So equation number 1, it says VF is equal to I2 times R. So we know our I2 that is free of any other variable. It is mostly on in terms of impedance, right? It's not dependent on I1, unlike I1, which is dependent on I2. So I2 is not dependent on I1, so we can directly take this and substitute it into formula 1, right? So that is going to give us this particular term times this, right? And then we can make VF upon V0 the subject of the formula, right? So if we make VF upon V0 the subject of the formula, we'll be basically getting negative JRXC upon R squared minus 3JRXC minus XC squared, right? Then what we need to do is, we know, remember this XC, right? This XC is not directly, I mean, it does not, this XC is basically equivalent to 1 upon omega C. So in place of XC, we can substitute 1 upon omega C into this same formula, right? And we can further simplify it. So if we further simplify it, we get VF upon V out equivalent to 1 upon 3 plus J into R omega C minus 1 upon R omega C, right? Next is this, remember this imaginary part is basically going to, this particular part is basically going to induce the phase shift, right? So we have basically proved that VF upon V0 is equivalent to this particular term over here, right? That is what we had to prove. So basically we have proved that. Next is to show that the frequency of oscillation is F is equal to 1 upon 2 pi RC, and the gain must exceed 3, right? So next what we need to do is, we know that this particular term over here is going to induce a phase shift, right? Remember, capacitance induces a phase shift between the voltage, the capacitive current and the voltage, I think, isn't it? You might have learned this in EE 102 and in your physics, in your Form 7 physics. There is a phase difference between the capacitive voltage and the inductive voltage, right? When you compare to the normal voltage input. So in this particular case, for the phase shift to be equivalent to 180 degrees between VF and V out, imaginary term of VF upon V out must be equivalent to 0, right? Remember, when we are talking about, okay, when we are talking about this particular phase shift second, remember I told you that these RC branches basically contribute 180 degrees phase shift, while the op-amp contributes the other 180 degrees phase shift. And when you compare your input to your output, the phase shift is basically equivalent to 0 degrees, right? So we know that these RC branches are going to contribute 180 degrees of phase shift. So in this particular case, what happens is, this particular term has to be equivalent to, I mean, is going to give contribute a phase shift of 180 degrees. So VF upon V out, this imaginary part, right, has to be equivalent to 0, right? The imaginary term has to be equivalent to 0. So what we do is we take this particular term and equate it to 0, right? And we can solve for omega. So if we take this particular term, the imaginary part, and equate it to 0 and solve for omega, we'll get omega is equivalent to 1 upon RC, right? And then we know that omega is basically 2 pi f, right? So in place of omega, if we substitute 2 pi f and make f the subjective formula, we'll get f is equal to 1 upon 2 pi RC, right? So that is how we prove that f is basically equivalent to 1 upon 2 pi RC, right? Next is to prove the gain of the second has to be greater than 3. So this is the frequency of the oscillation. Substituting the frequency, right? Substituting this particular frequency into Vf upon V naught, right? Expression we get. So this, remember, we have equated the imaginary part to 0, right? If we take this frequency and substitute it in this particular term, the imaginary part will change into 0, isn't it? So in that particular case, what happens is Vf upon V out becomes equivalent to 1 upon 3, which is equivalent to beta, right? This shows that 0 degrees phase shift from V out to Vf can be obtained if f is equal to 1 upon 2 pi RC, right? The gain of the feedback circuit becomes 1 upon 3. Therefore, the oscillation takes place if the gain of the amplifier exceeds 3. Remember, this is our beta, which is equivalent to 1 upon 3. So the loop gain has to be equivalent to, based on the Bocosian criteria, right? Based on the Bocosian criteria over here. Bocosian criteria over here. Wait. Over here, the loop gain has to be equivalent to 1. So in that particular case, we know that our I times beta is equivalent to 1. So our beta is equal to 1/3. So our I has to be equivalent to 3, isn't it? So in order for the oscillation to take place, remember, based on our labs, we know we have to slightly increase the gain, isn't it? So in this particular case, we increase the gain of the circuit such a way that it exceeds 3, right? So in that particular case, our gain, the loop gain or the open loop gain has to be, or the gain of the amplifier has to be equivalent to 3, right? So gain of the gain of the amplifier has to be equivalent to 3 because the feedback has a gain of 1 upon 3 in order to satisfy the Bocosian criteria, right? So in this particular case, the gain has to exceed 3 in order for the oscillation to take place. So anyone has any questions? I believe it is all mathematics, so it is slightly difficult to explain, like going into like I won't be able to directly show you the substitution, right? However, I have passed out the solution in the Dropbox. Is that fine? In the chat box. So you guys can download this solution. So anyone has any question?
No, sir.
Okay. So with this, we have come to the conclusion of the tutorial. I think most of you are here just for the attendance, isn't it? Because I actually can't see anyone participating in the tutorial or like saying anything in between either. Like no one is raising any sort of queries because I know I did make a couple of I mean, there could have been a couple of more clarification that you could have asked, but most of you are here just for the sake of attendance. Am I right? I mean, there's another factor. I mean, I do understand that you guys have already attended this, so it becomes like a boring class because you have already submitted the whole solution, isn't it? Okay. Okay, so we'll end the session over here, right? Okay. So have a nice day and a good weekend. And I think the short test is next week.
14, sir.
Week 14. Okay, yeah. So you have ample time. So prepare for your short test as well. So yeah, so we'll end the session for today. Bye for now.